This video will also be in 3.1. We'll be talking about intervals on which the function f is increasing or decreasing. We just talked about finding critical numbers. We'll use that to help us answer these questions. So let's start with number 15 here. F of x is equal to 2x minus 3. Our domain is negative infinity to infinity. Here, since it's a polynomial, f prime of x is equal to 2. And that never equals 0. So there are no critical numbers. If I look at the slope on the number line here, f prime of x from negative infinity to infinity is always positive. So it's going to be increasing. When the slope is positive, the function is increasing. It's increasing from negative infinity to infinity. Should have been that from the graph here, that this is a linear function, the y-intercept of -3 and a slope of 2. Then we go up 2, right 1, we would be at 1, -1 there. And we have positive slope that's increasing from negative infinity to infinity. Let's look at number 17 now. And that is y is equal to x squared minus 6x. Again, my domain is negative infinity to infinity. And sorry, y is equal to x squared minus 6x. Y prime is 2x minus 6 is equal to 2 times x minus 3. We're going to set that equal to 0. X minus 3 equals 0. X equals 3 is a critical number. Let's put 3 on my number line. And we're going to test 2 times a number less than 3. So like 2 times 0 minus 3. 2 times -3 is a -6. And then I'm going to stick in a number bigger than 3, like 4. 4 minus 3 is 1. 2 times 1 is a +2. So we're decreasing on this interval, increasing on this interval, decreasing from negative infinity to 3. Open intervals for both of these. We don't include the endpoint because we're neither increasing nor decreasing at 3. Increasing from 3 to infinity. All right, I'm going to clear the screen here. Move on to number 23. So let's come on down here to 23. F of x is equal to x to the 4th minus 2x to the 3rd. Come on. There we go. X to the 4th minus 2x to the 3rd. My domain is negative infinity to infinity. F prime of x is 4x to the 3rd minus 6x squared. I'm going to take out a 2x squared and make that 2x minus 3. I'm going to set that equal to 0. Say 2x squared equals to 0, or 2x minus 3 is equal to 0. X squared equals 0, x equals 0, multiplicity 2. Tell you why I care about the multiplicity in just a second. 2x is equal to 3, x equal to 3/2. Put those on the number line. 0 is to the left of 3/2. And I'm going to look at the factored form here when I stick in a number less than 0, like -1. -1 squared is 1. 2 times 1 is 2. 2 times -1 is -2 minus 3 is -5. 2 times -5 is a -10, so it's negative here. The other side of 0, let's stick in 1. 2 times 1 squared, that's 2 times 1 is 2. 2 times 1 is 2, minus 3 is -1. Positive times a negative is a negative, and look, there was no sign change, even though it was 0 here, because there's an even multiplicity. It did not force a sign change. I go on the other side of 3/2, like x is equal to 2. 2 squared is 4. 2 times 4 is 8. 2 times 2 is 4. 4 minus 3 is 1. 8 times 1 is a positive 8. And there was a sign change there because there's an odd multiplicity. So we're decreasing from -infinity to 0, union 0 to 3/2, and we're increasing from 3/2 to infinity. Do not say this is decreasing from -infinity to 3/2. That's wrong. It's neither increasing nor decreasing. At 0, it leveled out. It was decreasing, stopped decreasing for a split second, and then continued decreasing, and then it turned around and started increasing. It looks something like that, but it's neither increasing nor decreasing. It has a slope of 0 right there at 0. All right, let's go ahead and look at number 25 now. The function g of x is equal to x plus 2 quantity squared. We're going to use our chain rule here. Now this is still a polynomial. It is a quadratic function with its vertex at -2, 0, and it has the same shape as x squared. It's just been transformed by moving it 2 to the left. So my domain is -infinity to infinity. Knowing the shape here, we should know that it's decreasing from -infinity to -2, and it should be increasing from -2 to infinity. Let's use calculus to prove that to us. G prime of x is equal to 2 times x plus 2 to the first times 1 is equal to 2 times x plus 2. We're going to set that equal to 0. So x plus 2 is equal to 0. X is equal to a -2. Let's put that on the number line. There's -2. When I stick in a number less than -2, like -3, 2 times -3 plus 1 is 2 times -1 is a -2. So that's negative and it's decreasing. Stick it in a number bigger than -2, like 0. 2 times 0 plus 2. 2 times 2 is a +4. It's increasing on this interval. So like we already said, decreasing from -infinity to -2, increasing from -2 to infinity. That was number 25. That was 25. Let's look now at 27. 27 says g of x is equal to 2 times 5x minus 1 to the third. This is a polynomial again, so my domain is -infinity to infinity. G prime of x is equal to 2 times 3 is 6. 5x minus 1 to the second times the derivative of the inside is 5. That's 30 times 5x minus 1 to the second. We're going to set that equal to 0. The 30 doesn't matter. 5x minus 1 is equal to 0. 5x is equal to 1. X is equal to 1/5. We had a exponent of 2, so there's a multiplicity of 2 on this answer right here. So when I have 1/5, a number less than 1/5 would be 0. Let's put 0 in here. 6 times, or 30 times 0 minus 1 is -1. 30 times -1 squared. That's going to be 30 times 1 is a +30. Stick in a number bigger than 1/5, like 1. So we have, actually, let's just stick in 2/5. That's not going to be bad. So let's stick in 2/5. So 2/5 times 5 is 2. 2 minus 1, 1. 1 squared, 1. 30 times 1 is +30. So we stuck in 2/5 over here and 0 over there. Got positive numbers for both of them. So we're increasing from negative infinity to 1/5, union 1/5 to infinity. We're not decreasing anywhere, and the slope is 0 at 1/5. Okay, let's go ahead and look at number 29 next. There we go. Y is equal to x to the 1/3 plus 1. And my domain here is going to be all real numbers. I can take the cube root of anything that I want to and add 1 to it. Let's go ahead and find this derivative. Y prime is equal to 1/3 x to the negative 2/3 plus 0 is 1/3 x to the 2/3. Remember what we said about critical numbers? Haven't found any like this up to this point, but they can make the derivative equal to 0 or undefined. So we're going to look for where the numerator is 0 or the denominator is 0. Clearly the numerator is never 0 here. Let's check out that denominator. 3x to the 2/3 is equal to 0. X to the 2/3 is equal to 0. If we cube both sides, x squared is equal to 0. Square root both sides, x is equal to 0. So let's make absolutely sure here. If I stick 0 in there, the cube root of 0 is 0 plus 1 is 1. There's actually a point there. So that's good. At 0, the derivative is undefined. But let's check a number to the left of 0, like -1, and that's going to be -1. So this should be 1/3, and it's the cube root of x squared is the way that I need to look at that 2/3 power. So -1 squared is 1, the cube root of 1 is 1, 3 times 1 is 3, and I have 1/3, so that's positive, and it's increasing. When I stick in 1, 1 squared is 1, the cube root of 1 is 1, 3 times 1 is 3, I have a positive 1/3. This was 1 and -1 that I tested here. So it's increasing and increasing again. So we have let's see here, x to the 1/3 plus 1 looks like this, where it goes vertical for just a second, and it's increasing and then increasing again, increasing from negative infinity to 0, union 0 to infinity. So x to the 1/3 power, the cube root of x kind of makes this S shape like that. That was number 29. Let's go ahead and look now at number 31. '31 says f of x is equal to the cube root of x squared minus 1 or x squared minus 1 to the 1/3 power. So this is going to be, I can stick in any number for x that I want to here because I can take the cube root of positive or negative numbers or 0. So there's nothing wrong with sticking in any x value here. So my domain is going to be negative infinity to infinity. And then we're going to get the first derivative here, f prime of x is going to be 1/3 of x squared minus 1 to the negative 2/3 power times 2x. So that means f prime of x is equal to 2x over 3 times the cube root of x squared minus 1 quantity squared. So let's go ahead and look for zeros of the numerator and denominator. 2x equals 0, or 3 times the cube root of x squared minus 1 squared is equal to 0. X is equal to 0, or can divide by 3 there, and the cube root of x squared minus 1 squared is equal to 0. Cube both sides, and I get that x squared minus 1 squared is equal to 0. Square root both sides, and I get that x squared minus 1 is equal to 0. X plus 1 times x minus 1 equals 0. X plus 1 equals to 0, or x minus 1 equals 0. X is equal to -1, or x is equal to 1. So let's put those on a number line. -1, 0, and 1 are my critical numbers. Testing a number less than -1 is going to give me a negative over, and this number down here is always positive, because when I square a negative, I get a positive, and when I square a positive, I get a positive. The bottom is always positive. The sign of this depends totally on the sign of the numerator. So 2 times a negative number is negative. 2 times a negative number is negative. 2 times a positive number is positive. 2 times a positive number is positive. So we have decreasing, decreasing, increasing, increasing. And so we have at -1, we would have I think it comes to a sharp point. It does something like this, -1, 1. So it's, let's see, decreasing and then still decreasing. So let's see, decreasing, then still decreasing, and then at 0, it changes to start increasing, and then it levels out, and then it continues increasing. It looks something like that. So but since the derivative is undefined at -1 to 1, it actually has to go slightly vertical. So it has to go more like this, decreasing, decreasing, and then increasing. It has to go slightly, it has to go vertical here. Let's do the best of my ability to get that to go slightly vertical there at 1. So it's got to do something like this. Right? So decreasing from -infinity to -1, union -1 to 0. I know that the book says just -infinity to 0, but that's, I guess that's technically right, because I'm going to -infinity here. That this is undefined, but it's because it's going to -infinity, which is still a negative number, which is why that they're saying that this is still going down and increasing from, and they're going to say from 0 to infinity here, because this is going off to infinity, but it's still a positive infinity here. So they go left to right. So that's why those have been mashed together. All right, let's go ahead and look now at number 33. G of x is equal to x plus 2 to the 1/3 power. That's going to give me a graph that looks something like this. It has a sharp point here at cusp. So my domain is negative infinity to infinity. G prime of x is equal to 1/3 x plus 2 to the negative 2/3. G prime of x is equal to 1/3 at cube root of x plus 2 squared, and so this is, no, I'm sorry, I drew the wrong thing. This is this shape again. There we go. So we're going to be increasing and then increasing. So take 3 times the cube root of x plus 2 squared, set it equal to 0, and divide by 3, cube both sides, x plus 2 squared equals 0, x plus 2 equals 0, x equals negative 2, multiplicity 2, so I don't expect a sign change, and that's going to be negative 2. And when I stick that in here, a negative number squared is a positive number. Positive divided by a positive is positive. Positive number squared is a positive. A positive divided by a positive is a positive. This is increasing and then increasing. And because that's going to positive infinity there, we're going to say that it's actually, see, now they do say that it stops there. So book says that it's increasing from negative infinity to negative 2, union negative 2 to infinity. So I would, on the last problem, then separate it where it goes to infinity like that and put the union symbol in between. They're being inconsistent on how they are answering these, whether they include infinity or not. So go ahead and leave that in there for that that one on 31, I would say, and ask your teacher how he or she wants you to answer that if you have a question about that. I think we're going to wrap up here. No, we've got 2 more. Let's look at number 43, and we'll look at 47 to wrap this up. So more of the same, but some more interesting functions here. For 43, now we have a rational function instead of just a function that was all on one line to start off with. 2x over 16 minus x squared. I have a restricted domain here, but I can't have 4 or negative 4. So those asymptotes will be important to me later, but they're not going to be critical numbers. So when I take the derivative here, the derivative of the top is 2 times the bottom is 16 minus x squared, minus derivative of the bottom is negative 2x, times the top is 2x, all over the bottom squared. F prime of x will be 32 minus 2x squared, and then minus a negative is a positive. 2 times 2 is 4. X squared over 16 minus x squared. Squared is 32 plus 2x squared over 16 minus x squared squared. So my numerator has a common factor of 2 and is x squared plus 16. Well, there's no zeros of that because that's a sum of squares. And then we have 16 minus x squared squared. So while we have zeros of the denominator, those are not in the domain. They're not critical numbers, but they are vertical asymptotes that I'll need to consider to see if the function changes behavior at them. So I have -4 and 4, and I'll represent those with broken lines like a vertical asymptote. And I'm going to put VA there just so that I know there's a vertical asymptote there. And on the interval from -infinity to -4, I know my numerator is always going to be a positive number. If I stick in something less than -4, this is a number bigger than 16. And 16 minus 16 will be a negative number, but then I square that negative number and get a positive number. So this is positive and is increasing. I stick in a number like 0, this is positive, this is positive, and a positive squared is positive, so this is positive and increasing, and stick in a number like 5, that'll be positive, that'll be a negative squared is positive, and so it's increasing from -infinity to -4, union -4 to 4, and union 4 to infinity. No critical numbers, but discontinuities, like I said, at -4 and 4, those are vertical asymptotes. And then these are my intervals on which it's increasing. Okay, let's wrap up here with number 47. Number 47 is a piecewise defined function. So y is equal to piecewise defined 2x plus 1, x less than or equal to -1, x squared minus 2, x greater than a -1. Let's look at that graph. That'll help us figure this out a little bit. So at -1, 2 times -1 is -2, plus 1 is -1. I have a solid dot there, and I have a slope of 2. I'm going to go up 2 and right 1, and this piece goes in that direction. It's linear. At -1, -1 squared is 1. 1 minus 2 is a -1 again. And there's that open circle, and that hole covers it up. And I have a piece going to the left here. So when I stick in -2, -2 squared is 4. 4 minus 2 is 2. I have 1, 2. And this is quadratic looking. So it's going to rise with that kind of a shape there to the left. Its vertex was at 0, -2. So its vertex is down here somewhere. And this is always decreasing. And then this is always increasing. And let's prove that with my derivative. Don't include the -1 because there's a sharp change in the direction of the graph there. It won't be defined because the limit from the left and the limit from the right are different. So we have, this is 2 when x is less than -1, and this is 2x when x is greater than -1. And so we have, let's see here. Oh, I drew these backwards. That's my fault. Less than -1 is a slope of 2. So that was less than, and then we go 0, 2, we're going to turn, and we're going to go up here, symmetric about that. It looks like that. That's better. All right, so we have, it's definitely from -1, and then we have 2x equals 0, gives a critical number of x equals 0, which is in my domain for this piece because 0 is greater than -1. So that counts. Anything less than -1 has a positive slope of 2. Between -1 and 0, stick in a negative number like -1/2. 2 times -1/2 is a -1. That's negative. Stick in a number bigger than 0. 2 times 1 is a positive 2. So we have increasing, then decreasing, and then increasing, which is what my graph does here, increasing, decreasing, and then increasing. So we're increasing from -infinity to -1, union 0 to infinity, and then decreasing from -1 to 0. So that is it for section 3.1. We'll come back next time and talk about 3.2, which are extrema and the first derivative test. Extrema would be local minimum and maximum points, high points and low points. These places where the graph turns, like right here is a local minimum. And how can we use the same test that we've been doing, but identify the local minima and maxima? It has to do with that idea of, I told you, when there is or isn't a sign change is what we're interested in. So there's a high point right here. There's a low point right there. Maybe you can figure out from the sign pattern how we would know when the graph reaches a high point and when it reaches a low point when it turns. All right, we'll come back and we'll talk about that next time. See you for the next video.